So I come from the mining and minerals background, consulting on projects as a quality assurance officer.
Okay.
And the Canadian Welding Bureau welding inspection is my forte, I guess.
As like an engineer?
Well, I consulted 2 engineering houses, so my qualifications is in basically welding and metallurgy and welding inspection and that type of thing. Processes and piping systems.
Cool. What's your educational background? Just
I graduated from Moncton College there and did my welding inspection and welding.
Me too.
All that stuff through there, yeah. So I'm a CWB level 2 welding inspector, technically.
Okay. And then you've dove into doing like the fluid dynamic stuff. I've seen some of the things you've been discussing, and it's really compelling.
Yeah, I have a natural propensity to that. My dad's an engineer. He still does. He designs food processing equipment and stuff. So, major industry was my thing. I grew up in it, right? So.
Welcome to the March 12th edition of the Electric View. I'm Neil Thompson. Today we have Richard, Dave, Cameron, Buddy, Jim, Eugene, and the wonderful Chris Monk Sellye, who has come to help us visualize the occurrence of the Earth in space and show us how simple electrical and Newtonian rules generate complex resonance shapes. Please take a moment to like and subscribe.
David, stop interrupting.
Sorry.
He's obviously excited.
Yeah,
Well, lately, the thing that really kind of blew my mind.
Out, so.
I took Google Earth here a few weeks ago.
The whole Google Earth? Wow.
Yeah, I took the old Google Earth and I said, okay, well, the polarity of it is north to south, and it's actually reversed, right? So the North Pole magnetically is on the south, and vice versa. And I just started plotting out the polarity following, the magnetic field, because I started looking into these reversals, right, to see what can I draw out of that. And inevitably, what I ended up doing was mapping the telluric currents that go around the entire planet, and it seems to be this twisted toroid with a torque. And
wow.
So I came at it from a different direction, but what I ended up actually drawing out, modeling on the surface, was exactly what Bruce, I think his last name is Laybourne, has done.
Right.
But I wasn't aware of his work. Right, I never heard of him until a couple of days ago, right? And I was like, okay, well, I guess he's already done it, but that's really cool that I came to the same layout, exactly the same layout.
Really? That's actually pretty cool that he came to the same conclusion.
Yeah. Wow.
Or relatively,
I can show
even
here.
Yeah, because that's something that's on the table right now that we're looking at, and we'd love to have you take a look at it as well. So just as far as starting a project,
there was a lot of talk about that. I assume the SO conference had something going on about that. The idea of because most people know there's like 4 magnetic poles on a magnet, one north, one a strong north and a south one right together, and then of course a strong south and a weak north right together. And this is likely something that's when the magnetic field begins to deconstrict, or the currents become equal, so to speak, according to what Richard's model would say, they begin to spread out and split. And we're seeing the polar vortex do that thing where it's coming down a lot more right now as the field weakens. So maybe that's maybe that's going on.
Right. So what I did is I basically started down here at the south, and I said, well, I see this, the Fibonacci sequence here, the spiral going on, and I started just going with polarity, positive, negative, and I said, well, that's a delta Y connection down here. And I just started plotting where I saw it repeating itself. And so why this formation was here, but in the past it was here. You can see where it's traveled across the surface. And I started following that track. It was here in this circle here. And eventually it just led its way up right into this delta Y here at, I guess that would be in Kenya, right? Mount Kilimanjaro and so forth.
Mm-hmm.
And this giant Y here. So I started mapping geologically and the polarity of it. And obviously it turned into a big transformer when that was done, because the resistance went through the sand here and ended up being polarized into China, which is the craton, right? The North Craton of China is a giant delta Y, where it's kind of fixed. So it seems to me that the surface is rigid in a few places and everything else kind of flows according to the current. You get large negative ion zones where the growth is, and the positives are the dries. In these delta Y configurations, right? Like all of Australia is a big positive coming in from 3 different directions. So that's kind of how I ended up accidentally doing the same thing that Bruce had come to.
Wow.
And in the top, you get that. There's the hex, right? The hexagonal coming in at the top.
So what data are you using for this?
I was just using my own common sense to, map it. We're using the polarity, right? So I just kind of started with the positive and the negatives, and just tracked it out.
Oh, I see. And so you're modeling it with the. Just describe like the thought process on the formation.
But where do you get the positives and the negatives?
Just from the magnetic field. So I just said, okay, this is polarized in a positive magnetic zone, right? And there seemed to be this interface where I assumed that the oceans were a negative source, right? Salt water, because I had noticed that the M2 and M1 currents in the oceans, when the tides rise and fall, they cycle around these zones, right? It'll rise and fall like within a confined space, rather than going around the entire planet like a gravitational thing. It seemed to be more magnetic. So I just assumed that these delta Ys are these focal points, right? So there's a delta Y connection, and outside of that is a positive and a negative.
So you're looking at it from the geological features you're seeing?
Yeah, essentially, yeah. So there's a split, an actual physical split in the crust.
Yeah,
so there's
Now
a delta Y here, and that just so happens to be Easter Island. Go figure.
Yeah.
Right.
I get to go.
The other one that blew my mind was up here in Hawaii. So you get the Emperor's Chain, right? It forms this big delta. It's like a delta, right? Delta triangle, not a Y.
Right.
Now, I noticed that the force came from in this direction and split that right down the center. And you can bookmatch that. You take Y, like on this center line here, you take this configuration of chain of islands, you can actually invert it and fold it over, and it becomes an identical mirror image of the upper side here that leads into towards Alaska. Right?
And so that you've got the center of that circle down there is where the volcano is. In the Hawaiian chain.
This is the Hawaiian chain of Hawaii. And this chain goes in this direction through this delta circuit and ends up back up here, which is a pinch point where the entire crust is bent around that point in both directions equally. And you can actually take that and fold it back on itself.
Hello.
So it just became kind of a really profound, I think.
Yeah, that angle has always caught my eye. As if you take the line out from the big island out, and then there's that right where you have it, that angle coming off, right, and then up into the Aleutians. Right.
Yeah.
And then
you see my little handprint here? Can you see the hand?
Yeah, it's moving around. Right.
So I noticed that it's book matched in a fractal type of idea that I've been working on, where you got this chain of islands down here to Hawaii, and then you have this negative. That's the elevation here, so minus 12,000 feet. to 18,000. So this is what could be a ridge zone where it's been raised up, right? You just kind of hold that image in your head that kind of looks like a serpent or whatever. And you go to the north and you'll see it inverted upside down. If I flip that over, it's the same seahorse type of serpent shape, but it's in reverse, right? It's bookmarked. And these are mirroring
right?
Right, but it's which I thought was quite profound, and that led me into to explore around a little bit. Then I'll let you guys kind of carry on here, but this is obviously the area that Andy Hall and everybody's been really focusing on. And I started to notice the exact same thing down where the current went through the center in this sort of fashion. This is the butterfly. Andy looks on. You can take this mountain ridge here at King's Peak, flip it upside down, and drop it into this lake over here as an inversion, either side of the current. And the same thing here at Gannett Peak. Take that, flip it upside down, and drop it into this valley. And this little system here is a mirror image of this little system here, and it just keeps going and going and going. Right? So the positive versus the negative in a fractal type of sense. And then I noticed over
the Great Divide being the mirroring.
Yeah, exactly. Right, it's a polarized thing. So from a geological, coming from the mining and stuff, my thing was like, okay, well, I'm used to how we used to look for oil using electricity and electric shocks and sonic booms and sonar and stuff to find the deposits. So I started to wonder, well, what if we could just follow the current, right? If the formation, like Rashat's crater here,
that's been
right, is a dielectric, right? So this is granite, sands, so silica dielectrics and all that kind of stuff, right? Diamagnetic materials. If it grounded to this iron over here, which is all this is a giant mountain of magnetite,
right?
Then across the center, when I mapped that out, so if I considered this as a Helmholtz coil type of idea, right? The loop went through the ground and came back out and connected with the air. This cross section is the force through the center of that Helmholtz coil, and it actually literally, tried to invert the ground and pushed it in that direction. So I started noticing.
Yes, that one is really illustrative of the idea.
And the other one, I'll just see if I can Google it here. Get your opinion on this one. Because I know that Andy Hall had looked at this also in some of the stuff. So we've all seen this one, right? Thompson Crater, which is limestone with the dome, right?
Mm-hmm.
So it's limestone that came out of the ground and formed this dome in some kind of a blast scenario. When I researched this, the geology of it was that the trees in this area are about 400 kilometers around it or something like that, or 40 kilometers around it. For the first 40 years of their life, they grew at twice the rate of all the trees everywhere else. Right? So they had this huge input of energy, like a negative input, right, to help them draw up the water and nutrients. So they were charged in reverse.
That's actually something that we know from the rich soil that arrives around volcanoes, which makes things like Iceland, especially on the southern coast, habitable. Or I shouldn't say habitable, fertile would be a better word.
Right. Exactly right. It's that ionization helps them draw. It actually pushes the water up into the tree. Right?
In the 1800s, sorry for interrupting, but in the 1800s they used to do the same thing with. They had this technique, they called it, where they would try to electrify the ground, but of course people thought it was, some people thought it was real and other people thought it was charlatan stuff, but I honestly don't know. I just know that they did it. So
The telluric currents, they ran the telephone wires, right, using loop batteries. But one thing I noticed about this was this. I started getting on to the idea, okay, these things are coming in pairs and in opposite polarities, right? So you get an extrusion through the limestone where the positive went from negative to positive and pushed up and out of the Earth's surface. And on the other side, it went in reverse and dug a hole, right? So you get an uprising and cratering effect on the other side, sort of like what was the Devil's Tower. But so Potomsky Crater, I went looking around the area for its sister, and I found it down here. So there's the same dimensions. About 4 miles away or so, in the top of a mountain is where it connected to the other side. So I'm just kind of hypothesizing or theorizing that there was a connection between that point and this point at the same time. It blew out here and dug into an aquifer in the ground, created a lake on this side as a source of the aquifer and connected to the ionosphere or wherever. It's like a simultaneous zap.
Well, there is that loop idea with F80 Halls is supported by not only the evidence, but we recognize that loop currents are the thing that happens. Even Mr. Carrig was talking about the other day when we were talking about the step currents when a lightning strikes the ground. The width between your feet determines how likely you are to be murdered or be killed.
Yeah, exactly right.
Because it's the loop that goes through your legs, up through your torso, and back down that will kill you. Not, if your feet are together, you're like just one thing, so to speak, electrically.
Much safer.
Well, yeah, because there's a potential voltage spike, and the difference between your 2 feet's voltage between right foot and left foot would determine how likely you are to die, right? So,
yeah.
Which is the whole, that's how all the large animals got killed off, was the implication, of course. But anyway, moving on to your stuff.
So how do we stand? I always heard that you should, crouch over and bend over so that it, I don't know, goes straight through your butthole or something, the lightning. Literally, that's what I thought you were supposed to do. Bend over like an ostrich with your legs spread apart.
Honestly,
that's giving me a great visual.
I know, eh? But
I had to paint it out for you.
There's actually a chart. You can actually pick it up, just in Wikipedia and stuff like that. But basically, it's designed to basically show you how far away you can get from something that is striking the ground, depending on the lethal radius, so to speak. Because the amount of current hitting an area causes voltage spikes. Now, obviously, the ground itself, as we are talking about in this particular thing with our friend here, is that it does conduct current, but it doesn't conduct it instantly. There's a resistance. There's all this stuff to go out. So, as much as we call ground zero, if you want things to ground out faster, you need bigger grounds. If you want them better connected to your circuit, so a lightning arrestor or stuff like that. So, the issue, of course, when designing one of these things is how far away from the house should this be? How deep should it be dug? What is the cabling connecting to the ground to take a lightning strike, without blowing up?
Yeah.
All those type of things. So that's when you learn, okay, well, if a lightning strike is beside the lightning arrestor, how far away do you have to be from that before you're killed? That type of thing. Because if a lightning strike hits beside you, this is how we kill chickens, right? They go bok bok, and we just turn on a switch, and they're all dead, and because we have enough voltage across that floor to cause their the distance between their feet to be lethal, and that's that's how that goes.
So what are we looking at here? This certainly very accentuated Lichtenberg patterns, which we love, of course.
Yes,
high contrast.
I kind of took that basic idea using the Google Earth, right? And I was like, okay, well, I'll go to some of the geological sites that I used to use in the industry, and I downloaded the KML maps overlays for Google Earth itself using from the U.S. state geological maps and the map magnetic field for the planet, that type of thing. So I looked at it, and one of the first things that came to mind was Serpent Mound's historical site. They claim it's an impact crater, which I don't think it is, because this is the crater in the Lake Green here. The Serpent's Mound is way down in here, where that little tiny mound is that they made the serpent and the snake. Mm-hmm. So they probably saw that, right, and considered it to be a ritual site. Never happened.
It definitely would be holy. The snake went into the ground right here, boys and girls.
Right here.
Right here.
Right. This is where it hit, right?
Or this could be where the tail of that strike was. Like if it's a depiction of Venus, for example, as many Velikovskians would suggest, that would indicate that the damage was done by that object, which, because what would happen in space is that the tail would jump from point to point. And obviously it was jumping across the Earth, and then it was eventually intercepted by Mars, and then Mars was taking the hits for us, and yay, congratulations for the hero. The hero fights the dragon story is born, type of thing. But
exactly, I think that's why they put this here. Like this is zoomed in, right, to Serpent's Mound, and you get this round circle here, and it follows through the serpent, and there's a Fibonacci type of tail, a spiral tail. So started looking for some evidence of that. I was like, well, why did they put that there, and what is it trying to map out, identify? And so there's kind of like the serpent area here and the tail. The head's up here, the tail's over here, and they map it out. But I zoomed out a little further. I said, okay, well, I'm going to use the same philosophy. There's got to be a positive and a negative, two simultaneous strikes through the almost type of current loop with all the geochromatic process. So I saw that this one was here and to the south, and still within this big Lichtenberg figure is a positive. This one here. It's hard to see, but it's an aquifer, right? It's a fracture. This is a fracture zone. So a positive fracturing here in this zone here.
How far away?
Okay, well, there's 2 points. That is, let's see, that figures 100 miles, 107 miles. So I thought, okay, well, this is one of the focal points. So the energy hit here and blew this all out and created this ridge line, all there that in the fractal figures. And then almost a perfect straight line through that is a bigger one south of Nashville on the other side. So it kind of comes into play here. Right on that line up between them, right? So there's your division. And another strike in here. In straight lines, right? So there's definitely something to be said for what we're all thinking. Yeah. And I'm just trying to think of ways to how we would, given the knowledge that we have, and we all agree. I see areas like this whole entire area. It's all zinc, and also from the mineral and mining aspect, it's all zinc and so forth up in here with your silicates and zinc and a lot of water up in here. And down in the south of the canyon is your copper. So it's a giant galvanic cell. A huge battery, right? You connect Yellowstone, which is that's your reduction, your acid reduction, basically sucking all that out of the galvanic cell, right? Which you're reducing side on the cathode. The anode positive down here, copper in Grand Canyon, which basically turned all that sand into iron. Sandstone, ionize that instantly. It's a giant battery. Pump some salt in from the top here, right from the straight here, pump the salt water, and as a catalyst, and connect it down here to California, and you get yourself a huge energy factory. Whether that'd be safe or not, I don't know.
So from like a material standpoint, which it was always one of those areas where I never dove into heavily, but I was always compelled by. But you mentioned limestone, and do you have any insight into it? And it's like I'm seeing one of the striking features that I've noticed since I was a kid, but it's like the Bahamas and that blue, the loud blue in the Bahamas. This is apparently attributed to limestone. Do you have any?
Yeah.
You have any ideas about that electrically?
Oh, just the limestone is much like it's a neutralizer, right? It cleans. It's a natural neutralizer.
Plus,
it changes the alkaline, right? It's kind of like baking soda, right? You can use it to neutralize an acid.
Mm-hmm.
So it's part of that chemical, right? And it's the same idea. So in my mind, Yellowstone is highly acidic, right?
Mm-hmm.
All that limestone in between with the zinc-rich limestone, trying to neutralize it. So that forms this neutral line down through the center here. And you get the copper on the bottom end. And when the two connect, it's saturated, you get that cathodic reaction, a huge chemical reaction, battery. So that whole area would have built up charge over time, right? During, let's say, a wet season or something, and floods, and during the ice age, as it melted, it would have saturated that area. And coming out of the under dry ice, right? When you came out of that solar cycle, it just went zap. That's the way I see it.
There's some evidence that, as we know, there's for us to think about earthquakes electrically is something that's not unfamiliar to us. However, aside from Thunderbolts.info's wonderful expose on the possibilities, there is this issue with fracking, for example, when they explode and crack aquifers open and so forth to drain more oil and whatnot. But the thing that happens afterwards is that there are continuing earthquakes. Now, these are obviously significant, like much more than you would explain from falling rocks in a cavern or something, right? So we're talking the possibility then that they are eventually neutralizing as because these have been these pockets of water and oil have been separated for God knows how long, and they have their own potentials built up, and then you're cracking the insulative layer between these aquifers, and now they're grounding out to each other as they leak, and then of course this is going to create boom. Eventually you're going to have a ground out, and these batteries are going to discharge, as it were.
Yeah. No, it makes sense. It makes perfect sense to me. I did do some consulting way back. They used to send me the odd paper, like the engineers. They used to call me the scientist. Send it to the scientist. I don't know what he thinks. They sent me some. This is back 2009, probably 2010, about subduction. It was specifically about the subduction risk for the company that I was working with, and it was probably the third or fourth largest engineering company on the planet. And they wanted to know what I thought about subduction, and that was part of it because we were doing SAGD drilling, right? So steam assisted gravity drain systems where you drill down, pump in the steam, and you liquefy it and suck it back out, which is essentially not quite fracking, but close to it. And it leaves a negative void, right? So they were worried about the same problem. Like if you fill it with salt water, what'll happen? Because if you take the water out of Saskatchewan, which is highly rich in potassium and salt, and dump it into the mines in Alberta, what's going to happen? Right? To try to repressurize, right?
At least
because you have to kind of repressurize, right?
Oh, no. At least they're thinking about it, right? Like that's nice. Thanks for thinking about that.
Thanks for thinking about it. Yeah. Well, they had to try to repressurize. Once you suck out all the oil, you try to repressurize to stabilize the geology, right, to avoid exactly what you're thinking. Because there was some lawsuits that were sort of being threatened or pending at the time where communities were sinking, right? People's septic systems were sinking by about a foot a year, right? And they're breaking their pipes and backing up and whatever, right?
For good reason. People were basically they created these voids and things were starting to slide into them slowly but surely.
Well, this is it. Because the oil is always located at the pinch points of a salt dome or something handy at a salt dome. Normally, it's under the salt. Magically, of course.
If you want to look about what we're talking about, Dave, we're actually talking about the tar sands or thereabouts in Alberta.
Tar sands?
Yeah. If you
I worked in Fort McMurray for 12 years. Yeah.
And it will blow your mind.
Got my mouse.
I was actually consulting with AMEC Americas, which is one of the prime contractors for Suncor and Syncrude, and right there in the oil sands. So that's where I cut my teeth on all this stuff, which I find I've considered myself fortunate, right? Because I got to work with some of the best engineers and in the world at the time.
That's where you learn the most. Yeah.
Oh yeah, right.
And then up close and personal.
For as far as the eye can see, in some cases, because this was normally this would be impossible. What you're doing is you're basically taking oil from dirt, and that's economically unfeasible, except for when the price of oil went skyrocketing there. Things were like, "Yep, let's do it."
Yeah, if it drops below $70 a barrel, they shut her down.
Yeah. Then someone tweaks a knob at Wall Street and it all changes.
Yeah.
Oh, it affects a lot of things because obviously people from all over Canada go to Alberta to do this. Because that's where you could spend 6 months and make 50 grand or 100 grand or whatever.
Yeah, at the peak of my career, when I was still into it, I was pulling in on average 27,000 a month.
Nice, right?
Yeah.
That's what happens. I mean, the guys in the Gulf of Mexico that go in, the divers, depending on what the thing is, but the amount of money that they get, suddenly when there's a rush, it's amazing. Monthly.
Yeah.
Oh yeah.
If you're in the right place, at the right time, it's pay dirt.
Well, it's high risk and dirty work, right? The health potentials and risks are there. You're sucking in all that stuff all the time. Cancer rates are high. There's people dying all the time up there. It's you got to be really careful.
Yeah.
And obviously,
how long did you do that?
About 12 years.
Wow.
Before that, I was in manufacturing. Manufacturing with up here in Woodstock. Here, I'm from Woodstock area, and I worked with Metal Fab to build fire trucks. So you see them all over the Maritimes. So I worked with that company for a while, and eventually started on the ground floor as a welder, fabricator, fitter, and then I ended up in engineering, doing the design for the wiring harnesses and DC circuits in the trucks.
Yeah, cool. Yeah. This is where the buffalo used to roam.
Yeah. Yeah.
Like, seriously.
Yeah, there still are some buffalo there, yeah.
Well, that's true. Yeah, there's still buffalo here, too, yeah. But I'm glad that we didn't kill them all off. But
yeah.
But still, it is I mean, the only thing that made this even remotely feasible is because we didn't really pay attention to, we basically deemed that whatever animals live there were not, because we just didn't have large herding animals. So it was like, well, what are we really displacing? I guess became the question. Because this is like worms. We dug through the ground and basically chopped up a bunch of worms. That's what we did, grubs and stuff. Because this is basically underneath the topsoil. And you just go down a little ways and it's all dirty sand filled with oil. Like it's as if oil came from the heavens and poured down across the entire land. But it was just seeped in. And then dirt kept falling.
Have you guys ever looked at, I think it's Thomas Gold, was it Tommy Gold that did some theories on abiogenic oil? versus biogenic.
Oh, you'll find a lot of love in this crowd with that. Yes, we're definitely in the or at least most of us, I would say, are probably in the oil being created, which makes more sense in an electric universe anyway, because you're basically adding. You can add energy to a system. Like, we know that there's anomalies in these oil sands. Like, for example, that we found that dinosaur fossil, the one with that was almost perfectly preserved there. That with the metal, the turtleback thing. That creature's there.
Yeah, I was actually there when they found that thing. Eh? Yeah,
it was
crazy. right through the trailers, right? I was like, "Hey, they found a dinosaur sim crew, boys! Come on, let's go check it out!" Right? So, I was there when that happened. Yeah.
What's the story behind that?
There was a shovel operator, and he was digging through the sand, to take out the sand for processing, and stumbled across it. And so that looks weird. He jumped out and had a look at it, and he found this 35-foot. I can't remember the name of the actual dinosaur, but yeah. Some dawn of some kind.
And it was just, that's the idea. The way it looked like it was crushed. And we talk about this actually on the show, about like watching fossils get in like turned to stone, right? And that's usually a very high energy event. But in a lot of the stuff over Canada, it looks like we were just inundated with a ton of dirt. Now, unlike the dirt that landed in the Sahara and was sand, this stuff was like mixed with oil or something, but like here's a dinosaur just going doop 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 doop, and then boom, was just buried, just friggin' buried, and it must have been hot. Yeah. It must have been fairly hot because there's evidence that one of the weirdest things that they've noticed in here is they found this type of stone that is one of the rarest stones on Earth because it's oil infused into rock because of this process that we're talking about. It seems that it somehow left in this, and this is very. It's like oyster, how shiny it is, and the way it polished it looks. But it's just a stone with all this oil in different layers infused into it, and and it only happens here apparently. So it's weird how we're next door neighbors to America, and some things are just like, this is closer to what the Dakotas, I guess, would be the closest thing,
right?
In America, like in that area, the kind of the appearance of it, just beside the Rockies.
It's interesting because the amount of oil that's here is actually like we would be the third largest reserve on the planet, right? But they don't count the oil sands as a reserve because it's actually not you can't just pump it out in natural form as crude, right? It has to be processed. So, technically, there's more oil than anywhere else.
What's just a 50,000 foot view of what's the process of refinement of the material?
Oh, you just extract it in sand, and then you have to mix it with water and heat it to liquefy it, and then they use a lot of steam reduction processes and heat exchange, right? Vacuum to pull it out and all kinds. It's a fairly extensive process.
That's what makes it cost so much.
Yeah.
But it basically it's like how much would you have to pull out to make a value? How much is there versus how much energy it takes to actually get at it? Because each of these machines burns diesel, right? So
steam reformation. The problem is with this process. Yeah, it's the efficiency, right? For every barrel of oil that they get out of this process, it takes 2.5 to 3 barrels of water to get it, right? So it's because mostly it's steam processing, and we use cogeneration to run the plants, right? You take the oil out, and then you burn the oil to generate electricity to drive it's just a circle, right? A vicious circle. But
we have way too much water here, and that's why we're not screwed that way, which is a benefit too, because like 25% of the world's fresh water is here. We have too much. We can't get rid of it. It just flows out. It flows out, and goes south, and becomes part of the Mississippi or whatever.
One of the interesting things, I can say probably one of the most interesting things I consulted on. I had to actually fly a guy in from the States who was a senior metallurgist to help me figure out what was going on.
It's good to hear you talk. The States. That's Canadian right there. The States.
Canadian from the States. Yeah, from the States. And yeah.
What's about that?
Oh. Well, the problem I was called in on was we had a series of 2205 stainless steel tanks. They had half-inch and 3/8-inch steel, stainless steel walls on these things. There was like a half a dozen of these tanks, and they started bleeding this black goo coming out of the welds right around the seams. It just started bleeding this black goo, and it was starting like actual holes through these tanks. And all they were was really water storage and reagent storage tanks. So mostly just water and some other chemicals in it. And they didn't know what was going on, and this black stuff was coming out through it. So finally, we did a whole bunch of testing and laboratory tests and sent stuff for analysis. And it came back that what was happening was that there was sulfur-reducing bacteria in the water that we were pulling out for the mine, because this was a potash mine. It wasn't a refinery. So we were pulling the water out of the ground for the processing of the potash into fertilizer, essentially.
Damn, the magic school bus really went downhill.
Stopped in there.
Yeah, obviously this is like some educational thing that someone's making for kids, right? But it's like, boom, boom. I was like, I wasn't expecting that. It's like, is that a real school bus?
I have to go back and see that one.
Please let this be a normal field trip.
Anyway, you were saying, Chris.
What happened was, what happened was that the bacteria was consuming or eating the shells of the tanks at the iron, which, like when you weld stainless steel, you'll get, at the heat affected zone, you'll get like an iron deposit there, so to speak, right? It'll convert some of the iron and the stainless into more of a hematite.
Right.
But what happened was the bacteria was attracted to the iron, was eating the iron and reducing the sulfur, and then converting that into oil and seeping out through the tank. So the bacteria was turning the stainless steel into oil right before our eyes.
Straight up.
I was like, well, so there must be some abiotic oil. So this sulfur-reducing bacteria that we find in the oil deposits, like we actually use that bacteria as a measuring stick or a gauge to say how rich will that deposit be. If it has X amount of this bacteria in it, it's going to be more rich deposit.
I heard about this discovery. Okay, I heard about it, but I was like, it says Canadians discovered blah blah blah, and I figured it was a scientific discovery. No, it's an accident, just another friggin' accident.
Yeah, basically, yeah. So we knew the bacteria was there. Wasn't sure what it was doing, but in order to, it's a sulfur problem, right? If there's a lot of this bacteria,
sulfur, that bacteria and iron make oil. Well, guess what? There is a ton of that stuff underground. I mean, I wish Edwin was still on right now, because Edwin would go, "Kwa?" Because that's that's exactly what he was talking about. He thought it might have been nuclear or something, but not. I guess not oil related. I shouldn't put words in his mouth. We weren't talking about that, but still, either way, this is just enlightening, because this implies, this whole idea of puree dinosaur. No, this is some bacteria eating sulfur and iron and creating oil poop. Oh, okay.
Pretty much, yeah. Like from what I gathered, right? The bacteria will form a shell around itself, like in a cellular casing, right, to protect itself from the heat and the hydrogen and everything else, right? But it converts the metals and irons into the shell, which is and it's carbon, right? It's all that black carbon. Right, so now you have these bacteria in water with a carbon shell, hydrocarbon, right? And it basically, when these cells die and they start to degrade, they lose their charge, they just turn into basically oil or a form of it, right? So I think there's a little bit of both going on, right? I think there is a pretty good case for abiogenic oil in that sense as part of the recycling process. Right, the bacteria eat the rock and they eat the minerals in the rock, and they turn themselves into a carbon-based shell with an exoskeleton.
This is almost a Star Trek episode, you know that.
And the black goo thing, right? Basically, the black goo, the swamp is the black goo.
I was actually thinking of the Horta there in this original Star Trek there with the, living underground, and these are the eggs, Captain. My God, we're killing them. Type thing.
Yeah.
Dun, dun, dun.
Yeah, but it's true. It's true. I mean, I've seen it for myself. I was like, wow, that's pretty wild, right?
That's crazy.
Right? And I spent $30,000 in consulting trying to get that done. Yeah.
Black goo, living daimonic. Black goo. Well, I guess you stepped into something.
Black goo theory of everything.
Illuminated black goo in your food. Illuminated depopulation. Conspiracy confirmed. Illuminati. Right there. Bible prophecy. Here we go. Yeah. Going in deep.
Oh, that's what was that? An interesting story, because Robert brought this up. What was the, if you care to share at all, but the controversy with what is it? The flat Earth guys, right? The pathway. Quick overview. If you're interested in sharing that, but that's kind of Robert.
Brought
that up.
Well, I had a couple of friends that were kind of looking at it or whatever, and I started to. I was like, okay, well, I'll give you a hand, and I of course didn't believe any of it at all, right? And I thought, well, there might be something more to some of what they're saying as far as their conspiracy ideas go. But there's got to be some sort of phenomenon causing this huge amount of people to basically reject science completely, right? And I wanted to know, is it a scientific rejection? Are they so disgruntled with globalism or what's going on? They're angry at NASA, or they're angry at globalists, they're angry at everybody. And they're looking for something new. So they're regressing backwards to a flat Earth type of concept.
I love you, Chris. I'll tell you right now, that you've just defined right there. Like, so what did you know? Well, I was looking at some interesting fad. And then I decided to do a research project on it because I'm Canadian, and that's what we do. just want to go figure it out. Just listen to analysis and play around. There's no danger. Why not? You're free to do whatever you want as long as you're not being a dink.
Right. So that's kind of that's my approach to it. So I was like, well, if I go at it as an outsider, like I'm a globalist, and you guys are, I don't agree with anything you say, then I'd just be rejected. I wouldn't learn nothing. So I decided, okay, well, I'll take the approach of I'll go along with it and become a part of that community as deep as I can get, right? To try to find the truth. Who's behind it?
I remember you asking me questions about it. Like, what about this? And I was like, well, this is probably more explained with that. And then, what about this? More explained with that, probably. And then it's like, what about this? He goes, well, here, these are two things. Like, but you never really, you didn't do that weird thing that they usually do where you ask me questions. You were actually asking me questions about things that were hard to answer as opposed to really simple things like, well, then how do you I go, do you not know how to use a sextant? Do you not know how to measure stars in the sky? Do you know where the North Star is? Come on. Like,
all that stuff.
All that stuff. Exactly. But anyway, move on.
Yeah. Right. So I wanted to dig as far as I could into it. And I wanted to see, as far as things like the Curie temperature of oil and the dynamo of the Earth and the core, because I realized that some of that stuff is definitely in question, right? Scientifically.
Yes. That's what the stuff
with iron being above the Curie temperature, it can't maintain a magnetic field, so it can't self-generate one. And those things are really, there's some leeway there, right, for conspiracy. And so I wanted to know was, are they doing that on purpose? Is it a religious-based thing, or is it, self-supporting bias, confirmational bias, and delusion? Like, what is behind it? So that's where that's how I get into that. So eventually I went into it. I tried to help them as best as I could with modeling. It's like, well, I'll try and help you. Maybe what I'll do is I'll, model as much as I can in 3 dimensions, and you'll see for yourself that it can't be flat, right? And I'll do an Aries failure type of thing. That was my final approach. It's like, okay, I'll do the Aries failure, right? I'll fail to prove that it's flat, therefore it can't be flat, right? Mm-hmm. And that's when it kind of fell apart, right? They called me out on it. It's like, okay, right? So then they ejected me from the. Said, okay, you're a traitor. Get out of here.
I watched this happen. Like, it was around 2011 or so, but someone hit me with it, and it was like, it was a situation in a bar, and they were proselytizing. It's like, what are you proselytizing this thing for? And that's where my Neil knows that I have an ear for conspiracy ideas.
Oh yes,
but
I love them.
Do you think that this was something that was funded nefariously, or was it something that was organic?
Yeah, I didn't find any, like, they try to almost support the theory by, you'll hear the little hint of, it's a CIA thing or a PSYOP, or it's been done on purpose,
right?
Because, just that self-reinforces the conspiracy or the delusion of it, so to speak.
Right.
But that's not at all what's the case. The case is that there are people that are motivated, by YouTube channels and hits and money and corporate type of stuff. Right. It's just a motivation that I want to be something, or I want to be part of something bigger than I am, and I can make some money at it. And it's just kind of an organic, self-reinforcing bias.
Right.
I didn't find any evidence of a nefarious agency or some Soros organization funding it or dropping it as part of an intentional conquer through distraction or whatever.
Right. I mean, there's certainly, it's certainly well funded. I mean, it seems like it, right? They're pretty well funded.
Yeah. That's part of the goal,
right? Yeah.
Like this organization here, right? If they might not. There's crowdfund. There's some crowdfunding, and then there's obviously corporate sponsorship where you can get perks from like electrical companies and suppliers for free gear, right? To do your experiments. Right? So there are benefits to it,
right?
So.
I mean, they're playing with this toroidal thing for sure.
I noticed that.
Thematic.
Speaking of like environmental contaminants in the water, how about the birth control pills being dumped in the water, especially like byproducts?
Oh yeah, how it's affecting fish and stuff.
Yeah,
I've heard that.
Hey, Alex Jones tried to warn you guys.
The hermaphrodite fish are coming for us.
He warned you about the chemicals in the water turning the frogs gay, but you wouldn't listen.
I love it. But some of the things that, like, there is a sort of, I think the anti-intellectual movement was mentioned by Isaac Asimov, like, way back in, like, the 60s or 70s there, when he made that quote there, the strain of anti-intellectualism is sort of reinforces the idea that your facts are as good as my opinion, and that's not entirely true at all, type of thing. And this is why, as much as I like to wander out into the world, that sometimes I have to go, okay, what do I really know? Like, what are the facts? As much as I feel the weirdness about the moon landing, for example. I can't deny that they went to the moon. I'm just wondering about the first time. That's kind of weird. And why all those weird tests? Were they, what were they doing? Why were they a little cryptic or something? But that doesn't mean that they didn't actually go or something. It just means because there had to be, it's just like not knowing the space shuttle's original intention was to grab satellites. I had no idea. Why did you think that? You just thought it was a cool space
plane. That arm was
plane.
built in Canada,
Oh, I know.
That robot arm.
Me and Chris are probably had that burned into our head. The Canada arm is going to space. Woohoo! Like 1980, everyone were waving flags. Go, Canada, go.
Right.
Yeah, and what was the other thing?
Chris
the airplane
Hadfield's still
that Canada invented,
The Avro Arrow? That's still a soft spot. That's like the Library of Alexandria, man. We can't go there. No, it's okay. But yeah, we had this plane during the Diefenbaker era with what was it, Eisenhower type stuff, and we put a plane out that could do like Mach 3, and they were like, you can't build that because basically NATO was like, give us, and then it was like no. So it was just not. This was only like what, 58, 57, something like that.
Yeah, I think so, around that area. Yeah,
getting a three Mach 3 plane, a fighter plane too. Like that's crazy.
With Hall, that
with Hall.
scream.
So they chopped every single one of them up, like literally chopped them up. There's not one left. The only thing we have is
they destroyed them and buried them and sent them to Halifax, melted down the rest in Ontario. Yeah,
that's how much the United States did not want Bombardier or whoever or Avro to make a plane over Boeing. But I mean, it just happened to be one of those things that we had all the stuff that we needed in that perfect area. It just happened to be. This is also before the United States. The United States was really taking off. It's only been a few years after the war ended, and the quote unquote gigantic middle class boom. It was sort of just slightly lagging up here, if you know what I mean. We always sort of ride on the United States trends. We just sort of like there's always these trends, and then always gets like a lot of times trends get a Canadian feel when they cross the border. Like certain things are like, that's trendy, but how about like this?
Do it a little different spin.
Yeah, I don't know. It's like, well, we have Mardi Gras in Quebec. It's not Mardi Gras in, down there in New Orleans, right?
New Orleans, yeah. Cameron, what are you doing with these icons, man?
Sorry, what did you say?
Your little gravatar there.
Oh, the avatar with the caption "Mother of God."
That was the Mother of God. Okay.
Hey man, I have a running pattern. Every time I'm on here, I have a different avatar. That's I'll be wearing from.
Pretty fun. It's entertaining. I enjoy it.
What's the technical term for the loop that goes on a Mobius strip? Yeah. So if you have
I'm not seeing your screen right now. But
yeah, I'm only seeing. I don't know what I'm seeing.
Let's see.
I'm only seeing myself.
It's this guy here. Right.
So start sharing. And go.
There you go. You got it.
This here.
Right.
There, you see like a Taurus knot, like the Celtic knot.
Right? Yep.
All right, so that's in 3 dimensions. So that's just a knot that I've got switched to Taurus. I'll look at it. Profile here. So what I was thinking was there's 3 or 4 spots of those deltas on the Earth, right, where they seem to stay static. Those 2 are the 2 of the most obvious ones, and there's another one over in the China region where it enters back in and it remains static for a time. So I got thinking if the energy is a Mobius strip, you can't create energy, you can't destroy it. Right? It has to fold on itself. Conservation of wealth, conservation of energy, and so forth. You started rotating that. I wanted to know what sort of shape that would make.
All right.
And so that's kind of what I did here. If I rotate it and then freeze frame it in a whole bunch of series of frames, you'll see that that's the 3-dimensional shape of it. Is this out of form here. So what I did is to look at that in 3 dimensions. I started looking at Tony Peratt's work. Because you end up, if you look at that really close and you rotate that, I'll animate that. You see how it spins, right? See a toroid, there's 9 of them.
Right.
So the Tony Peratt plasma toroids are in that form. And it's only one form rotating on itself through this toroidal Mobius type of form. It's a 4th-dimensional type of thing. Anyway.
How are you doing? How are you doing the cylinder in the center? What's your map to that? Because I'm seeing like a plasmoidish kind of thing with the first thing, and then I see it. Right. I can kind of see it now. Yeah.
Right. So if I stop that, you'll kind of see that in that mesh, right? There's these. If you zoom in close, you can kind of see that if you move them around, you'll see that there appears to be a toroid in there in that mesh, right? It's
There.
becoming emergent, right? It's a self-emergent toroid.
Uh-huh.
And it's coming from that torus knot that's spinning, right? So if I spin just the knot, right, the knot is actually creating this form because it's spinning so fast.
Right. This was this plasmoid, stuff is just really plays, and then starting getting into the harmonic analysis of it.
Right. This is the harmonic analysis of a triple torus, right? So it can't collapse. The waveform can't collapse, otherwise there'd be no reality, right? We have to have it. So it only has one choice, is to polarize itself and go back in the other direction on 120 degrees to the three-phase circuit. Right. And so when I do that, you end up with these embedded. It'll form all of those shapes. And when I look at it from the top, and I'll stop the animation and just turn off the.
And there's 9 of those. Huh?
There's 9 of them. Yeah, there's 9 within that form,
right?
Which is the plasmoid, right? And you look at it from the top, and I'll turn those plasmoids off. And it's like, well, there's shells in there, right? There's almost atomic shells. If you zoom way into the bottom here, there's a minimum, and you get an inner 1, 2, 3 shells, right? Then you get a vacuum void, then you get another shell, right? And those are embedded spheres. So you'll end up with the shells of the atom. In essence, you have to look at it from the front again. It's like, okay, well, there's three more, right? So there's a positive and a negative inner toroid.
And there's the tropics too, right?
And then there's so there's basically you end up with the planet. Right?
Yeah.
All stemming from that one rotating field, like at crazy speeds.
Yeah.
Torque, counter torque, rotation, it's all in one form.
Pretty cool. That's really great. That's really great. There's infinite avenues of illustrating this.
So I'm trying to figure out, how do I relate that to the delta Y and the delta circuits in the planet and show that.
Well, this is what Bruce is looking. Bruce is on it. We'd love to have you join. Some of the conversations that we're just starting. So.
Let's see if I can find. There's one more. Recent Grand Canyon flux loops here, geomagnetic. Hopefully it opens.
It's like watching. Go ahead. I'm sorry. Stupid comment.
This is the three-dimensional elevation.
Right. Yeah, Robert was showing me some of these that you were doing. Yeah.
So to try to explain what I'm doing here with the Helmholtz coil type of idea, it's the same thing, keeps repeating in the Grand Canyon. Let's see, I'll go to solid view, might be a little quicker. I'm just trying to get it because I'm streaming this and doing this at the same time.
Yeah, wow. Awesome.
So I noticed the same thing, whereas if I take that torus, it should find it here in the model. All right, I can toggle that on and off, right? So you see the same polarity. What I've done is I've exaggerated the z-axis a little bit to make it easier to see. Right, so on this side, you have the upwelling polarity, positive coming out in a couple of places. Well, 3, 1, 2, 3. You get a mesa in the point where it was ejected out of the ground. And on the other side, you get the crater at the center of this vortex here, where it went back into the ground and created this entire region here. Right? It just boom. So there's the connections on either side. So I would assume that first one is probably a parent connection, and these smaller ones are residuals, right? So the energy came into the crust of the surface and then came out in these coronal fluxes and just kind of rattled everything and then nested. type of frequency.
They're just it's just induction-induced loops.
Right.
If you have a current going along the length of the Grand Canyon, so from and you're on the screen right now from the lower right to the upper left. Okay, not that way now. I guess now it would be from the upper right to the middle left. That strip is across those loops because it's a right-hand rule type of thing. If the current's flowing across the ground that way, as it would as the strike is occurring, these loops are induced, and they will have the same direction and the same polarity.
Right. So the force is going from right to left, connecting to the left side of the screen. There's another loop over here. It's a bigger one. And I noticed the same topology here that I saw at the Richat crater in Africa. This plate here is also tilted at about 15 degrees, right? So, and this here, right? So you can see that the force went from right to left, made the connection, and then the torque and the magnetic field fractured this plate and pushed it down on an angle, just exactly like it did in Africa. Right here at this ridge line. Right, it uplifted that and pushed it down. So there's the angle of the magnetic field that came from. You can see the pitch. Wow. So that's where I'm trying to get to a point is proving that, right? I mean, the evidence is there. It's just screaming at us, right? Screaming at me. Right. There's your magnetic B field. The B field went here. The current went, right to left. The B field forced it down, and that's it. It's game over.
This is absolutely amazing stuff.
Yeah, Chris, amazing. Definitely.
Yeah, I debate you on some of those interpretation of the land up and down because I see a lot more carving and etching because of the same thing that I see on Io and other moons and stuff like that. But given that said, I've never seen something on this scale at all. Yeah. Like really, I mean, visualizing this and comparing it to a small laboratory would not do it justice. Although we can see the comparisons when you amp current up, because the amount of current that would be required to make this canyon, for example. The loops that you're describing would certainly be more pronounced. And compared to, number one, it shows something that, in case we were ever wondering, remember we had that question, I wonder if the ground was being hit with AC or DC? This confirms it. It was hit with DC. Because otherwise those loops wouldn't exist. It could only occur if the current's going in one direction. There could be vibrations in there, other harmonics, obviously. That's notwithstanding. Andy saw the harmonics and waveforms blast against walls and everything else, and we see them on the ground. So that's notwithstanding. But there was clearly a positive and negative part to the Grand Canyon hit, just if this information is true, because those loops are showing the induction of this current as it has to go through. It's inducing these loops as it goes through. And of course, they're also going to induce their own loops in an opposite direction, by the way. Smaller, really, in the middle of their own, in the middle of themselves. And this is what leads to Arches National Monument type stuff,
Right. Yeah, that's kind of the way I'm seeing it, right? Is if you had the event like this is all being rattled earthquake, you got liquefaction, you got the arc going down through the center of that, etching it out, blowing, major dust storms, like just horrific dust storms into the sky, etching, and it would just be a nightmare, right?
Yes, everything in this area is dead.
It's saturated and it's saturated and wet, right? However, wherever these current loops are, the field, the magnetic field that comes with those loops temporarily stabilizes and heats those areas, right? So it temporarily just locks them in, and everything else moves around, right? Right.
And we see this in some experiments with die fly fish and other individuals where they're burning holes through certain areas.
Yeah.
and how they go across ground and then down into the earth and so forth. Or, well, I guess into the rock in the experiment table in this case. But
yeah, once I started connecting them in that fashion, it's like, okay, well, these things are everywhere, right? You just start going, connect the dots, start playing the dots. If I zoom way in here.
Is there a way to physically simulate this? Like as far as, obviously this is like lab scale, and get the same kind of geometry out of some material, kind of like what Billy Elverton does, etc. But a little bit more detailed, similar to what you've got modeled here.
The only thing I thought of was like a Helmholtz coil with plasma. Right? We've seen that, right? That's obvious. But I'm not sure how you would do it through, like if you had a Helmholtz coil set up with a couple holes in it so it could actually pass through a plate, put a plate through the center, and then put sand or something or saturated material on that plate, and then just hit it and see what happens, right? So you have a coil, and then with a plate through it, right, as a surface to represent the surface of the Earth. Because on the side view, what you got to replicate is basically that on the side view. It's going to be that sort of setup. Right? So he would need some Helmholtz coils to carry the current, sand, wet sand, whatever, right, and just hit it with a high voltage.
Yeah, I mean, I'm just seeing. I'm imagining kind of like a. I play around with synthesizers forever, but something that you would be able to get in there and tweak and see if you could come close to the geometries. Something that would be repeatable physically. Do it actually in the lab. Yeah.
Well, the trouble is, like we were talking about before, it's the same thing that when Anthony Peratt was trying to. Well, he wasn't trying to. He noticed the correlation between the stickman figure petroglyph and the stuff he was seeing in the laboratory. So that connection was made. But the trouble is that getting that in the laboratory still required high amounts of current. Time scales with distance and current can become diffuse over, cubic meters, of current.
Right.
But if you're going to do it in a laboratory, you have to concentrate it, and that's, well, as you can see, expensive equipment. Usually.
Yeah, well, if you start thinking about it scalarly, because that's kind of the theme that's going on is keep scaling down to where it's realistic, and if the theory is right, you get potentially you get to the scale where it's efficient.
Well, no, you're right in theory. The trouble with current is that if you're looking at a tube of current, and you have, let's say the stickman figure was sticking out of the southern part of the Earth, right? Of the South Pole, and it was a giant, cool arms to the sky type thing with the torus around it. Well, that takes 1.3 mega amps of current to make, but it didn't hurt as much stuff because that current was diffused over such a large area, but you'd still have to use that 1.3 mega amps of current to make that form, but you have to do now
on that scale
on a small. But no, but
yeah.
Even on a small scale, you still have to do that same current to get that form, or you just have a smaller.
I argue not.
Oh well, I was just going with Peratt stuff, but I could be wrong on that. That's CS. That's Jim.
There, can you see it there now? I guess.
Okay. I can. Yes, indeed. Let me blow this up.
All right. Let's see, hurricane. So I'm starting basically with a hurricane map, right?
Mm-hmm.
The globe. And it's a historical one. It goes back, I don't know, a decade or so. All the hurricanes. Actually, I think it goes back further than that.
That's actually very interesting.
Right, so you can see where these kind of spawn out in the middle of nowhere, because I've sent a picture to the group there, and you can see there's a gap in the chain, right? So there's this inner ring. That's what's a split ring of energy. When you lay it out flat. But.
Well, yes, clearly, I can tell that you have an angle. The reason that this is very interesting to me suddenly is, do you ever hear that? There's a video called Revelations of the Pyramids. And in that video, the original was narrated by the actor Brian Cox. Not the science guy, but the actor. Because he has a deep roguish voice, kind of cool. Anyway, that shows a 30-degree incline in the other direction from this. Or maybe it is this 30-degree incline. Oh, now I'm all concerned. This is a 30-degree incline.
This is I got the Earth stationed the way it should be on 23.4 degrees tilt to the ecliptic, right? To see if the in any way orbits would have any influence on Coriolis.
Well, yes,
that does have a bit of effect, right? But I'll show you where.
Well, yeah, it can have an effect, but I'm not. I mean, I'm not nearly as. We're dealing with charged bodies between two plates of charge. They're going to probably be moving due to electromagnetic forces a bit more than just, wind.
Right. So that's where I'm going with this one here. Is right. They start in the middle of nowhere, and then you connect that with gravitational overlays, right? So you can see that this blue zone here is a negative, right? So there's lower gravity and magnetic activity, and the same over here off the coast of the United States. And then you just toggle that on and off, and you see it. That's exactly where hurricanes start. It's down here in this zone down here.
Well, this seems exactly opposite, actually, now that I'm looking at it. I think it's opposite. This is really hard to gauge exactly which direction things are going, because it's whenever you cross the equator or make an equator around the world, it's a circle, except when you look at it from just the wrong angle, if you know what I mean. Anyway.
The equator line's right down the center of the right. So if you go in from the G Gilbert up to this left-hand corner, that's your equator line.
That's the equator line right there? Okay.
Yeah, going across that arrow. But down here, right, to the right of where it says PAM 2015, where all these hurricanes are starting at the middle of the Pacific Ocean, if they start randomly in the middle of nowhere.
Right.
That lines up with the gravitational anomaly of this blue negative.
Is there any islands along that strip? Because that's where I would live.
Yeah, there's a few.
I would live right there, we don't get hurricanes here. Why? Magic. I don't know.
That's where they start, right? So that's the French Polynesian area, right? So that's like French Polynesia right down the middle of the Pacific.
That's where all those Godzilla was made?
It's like where all those basalt columns are, right? So they made the temple, right? So French Polynesia.
Oh, you mean it wasn't called.
Yeah.
It was polyp. I thought it had like PALAU, like one of those, or Paco or something like that. But yes, the basalt columns that are sort of stacked.
They make them all horizontally, like they stack them like Legos, right?
Yeah, like a castle, like a log cabin made of salt, basically.
Right. So that's right down in this area here, where that's all the lightning starts, right? Because when you compare so you got hurricanes in this area, following the gravitational anomaly and magnetic anomaly, and then you take that lightning right over with the lightning map. Obviously, hurricanes and lightning go together. Right, so this one's a comparison of your lightning map to the hurricanes again. Okay. You can see, obviously, hurricanes and lightning. So you get the three things mainly going on.
That's pretty damning, really, when you get down to it, because
all three
of them are
path, right? All three of them on the same path, right? Right.
Well, it's a lot easier to imagine. Well, the Earth, where it's water, is incredibly flat, and everything that sticks up out of the water only sticks up as far as the ocean is deep. Like Mount Everest, for example, is the highest thing, but the ocean is no deeper, well, a little bit more deep than that. But the point is that with that look to it, with that thing, the Earth is basically a very smooth sphere, and if we were to basically picture all the water as a metal, okay, a flat metal, and then sort of throw some dirt and or silicates around in the shape of these continents, I guess, I bet you we could remake that effect in a Torella, and we would see this exact thing, which is what I think Birkeland saw when he made these. He saw rings around. I mean, the connection between where it says Fentella 2016 and Paradip 1999 is across the equator, and that's exactly where we see those plasma loops that were discovered by that Australian student that basically bridge that gap. And of course, on the top of those loops is the Van Allen belts, right along that ring, right along the equator.
Absolutely, yeah.
So I mean, to not see this it would be hard not to notice.
It'd be hard not to notice, yeah.
Yeah. Especially with this ability of the time lapse. I mean, not seeing it in slow motion. I mean, we think of a lightning storm, and that's a big event to us. But if we were to look at Torella with these exact effects, it would just be like right across the continent, like that, like it would be gone. So these are just sparks as the charge goes through this body, and the Earth literally is crackling and humming, as earthquakes can attest. If you put them in order, I bet you'd see some interesting things there. I love this program, what you're using. I'm just fascinated by it. What's that big red black spot in the middle of Africa?
The problem is I couldn't find any, like Google Earth. Okay, you can download overlays for Google Earth, but they suck, right? So I couldn't really get the information I wanted. Right, so I just had to break down and go get the maps from NOAA and NASA and everywhere else, and then make my own model. Right, I just had to
wrap them around the Earth,
wrap around the ball, so I could see what's going on. Because it's hard if it's flat. You got different orientations and different scales, and it's like it's
if you're looking at planets, there's no better way than a sphere.
Yeah, because you're trying to envision, a conductive sphere, a Gaussian sphere, flowing through a magnetoelectric space, right?
Yeah, it has a magnetic field somehow, yes.
Right, and it's like, come on, quit showing me these flat maps. I can't do nothing with it. So this is exactly what you're saying. Like you were saying that the student saw the spawning here in a split north-south, right?
And he saw and there's loops, just like we were talking about in your other presentation. These loops, but they only go across the equator, and they're basically called plasma tubes to these people, but they're basically Birkeland currents that are bridging. And we've seen the exact same effect on a Torella.
He's Australian, I think. I remember.
Yeah, and if you see, I think Birkeland has a wonderful, little copy of it, So
yeah. Yeah, because they had noticed that the tubes were actually interfering with the focus in the Australian observatory, right? It's causing perturbances.
Because it's they're trying to find.
It's bending the light. Right?
Yes, exactly. I was going to say that.
There's a black hole.
Jason Verbelli was I shouldn't say lambasting because that's not the right word. He was correcting people when they said, "Hey, you want to see a magnetic field?" And he was, this person showed how to take some oil with some toner in it and put it between two plates, and then and then use lights along the edge to sort of shoot these lights up through, and then you could see the magnetic field. But he was right. You're not actually seeing the magnetic field. You're seeing the reflection of the LEDs through the light as the magnetic fields orientate the oil. So if you want more quote unquote lines, you just need more lights. And that's not exactly, he was right. You're not really seeing the magnetic field itself the way that you
the Faraday polarization is.
Yeah, that's what he's seeing. That's exactly what you're seeing. And I love the fact that you can actually see these physical effects. It's I think sometimes children are not exposed to that more. They perhaps maybe they reach a point of they don't have to think about. Maybe that's where the whole flat Earth thing comes from, where you're not sure what is real and what is not, because you've seen so much amazing stuff in your life that usually is on TV, of course. That seeing something in reality, like like a smoke chamber for the first time. I mean, the moment that someone goes, I bet you we can make a gas that could display any of these ionization fields that are coming from this, and the more we see it, the worse it is. And then, of course, Madame Curie was like, "Yeah, let's do that." And then they put a rock into the cloud chamber, and they closed it, depressurized it, and everything. And then suddenly they were just seeing clouds being formed all over the place. And then they realized, "Oh, we're so dead. We are so fucked." But like just seeing the real effect is what I mean. Like something that's tangible, physical, you can touch. Or if nothing else, at least a model of all the maps put together. This is what Ignacio does with space, by the way. You and him would probably really enjoy talking to each other because he does time lapses of space over like decades and tries to find differences in the film. You know what I mean? Of the same space.
Right.
It's very interesting.
Yeah.
And it's kind of like this, where you overlay different, here's a picture in the infrared, here's a picture in the, gamma ray and so forth. And so I got that feeling when I'm looking at this, except now the Earth is taking a much more horrifying approach. It's all it's bruised and battered. Is that what happens after we get done with it? That's what we're looking at here?
Well, this is where it gets kind of interesting. Where you said she saw the separation was, if I take, for example, so this is your gravitational anomaly, right? So this is where Bruce was very interested here in the Congo, because right here in that blue spot is the most lightning basically in the world. Essentially, I don't know if it still holds the title, but it used to hold the title for being the most lightning.
I thought it was in Venezuela.
It may have moved now, but it was there. It used to be in the Congo.
Well, that wouldn't surprise me, by the way. Because if I'm not mistaken, it's only around one lake in Venezuela, and it's high up, so I think that's probably why.
So there's the black spot, right? So that's the highest.
What are we looking at here? What's the map?
This is the lightning map, right? So lightning intensity, right? So you get this butterfly. So there's your butterfly in the Congo.
That's a connection right there. Where's
that's the connection? And then I was like, okay, well, there's a negative up here, a negative connection. What's that all about, right? So this
the equator
is
goes between them both, doesn't it?
Right through here, yeah.
Yeah, that makes perfect sense. But that's what it should do. I mean, that's a lot of land, and they're crossing over, and they're because these currents that you're seeing with the lightning maps and with the hurricane maps.
Skull in Africa.
Pardon?
I'm sorry to interrupt you, but it looks like there's a skull around Africa.
No, it's Deadpool coming out of Africa. That's what it is.
Well, this is your negative gravity zone, right? So on the gravity map,
right,
the magnetic map is a negative gravity zone, and you got a split there, right? So a positive and negative. You can see there a positive and negative ring on the split, right? So then when the lightning strikes on the lightning map, it does the same thing, right? It tries to pull that apart. So you get a lack of lightning here and a high intensity here, and there's a double split in your current. Right?
Well, of course. I mean, electrically that makes sense.
Right.
Yeah,
so you get really creepy.
And then in the north, you get the secondary, which is, so you high voltage here to low voltage here, right? So secondary on the transformer, essentially. And then you get another butterfly in the north, but it's a negative.
Actually, see, this is my problem with, and I shouldn't say problem because this is not true. That's incorrect. My issue with Bruce Laybourne, his stellar or his transformer idea, is very important to note that the Earth is, but also sucks as a transformer. Like if we were to build a transformer, we would make it way more efficient, and we wouldn't make it a ball.
It's bringing in millions and millions and trillions of volts, right? You're only getting about nanovolts out of the damn thing, right?
You're getting more than that.
That's an analogy, right?
Okay, fair enough. But what I meant was that it's kicking up the volt. Like we know it does do this because after Michael Claridge's work, he shows that the rings of the Earth, the Van Allen belts as we call them, expand and contract based on the amount of current the Earth has to process. It basically kicks them up into higher voltages.
Right.
This is probably something along that line, something that is one of the conduits, more or less stable conduits in that connection, that brings charge, because that line across the equator, you have currents coming in the north and the south, and they are working their way towards the middle to get to these 2 points, not just those 2 points, but all around that area, to ground out to the ionosphere, to that ring, the Van Allen belts that are around the Earth, which basically is the Faraday motor, the homopolar motor effect, but on a ball. And it's not a very good, it's not smooth. It's broken. It has issues. This is why, this is what I like to look at planets like, or moons, or anything like that now. I'm looking at from that point of view, like you are stuck in a tense electric field, and you're reacting to it. Go,
Well, yeah, right. Like it's because it's both creating and rejecting the magnetic field, right? It's a push pull thing, right?
Well, one of those are just, the only reason there's a polarity difference is because there's more. As Richard, our friend, was our guest here, is so good at pointing out, is that there is a connection right along that, where you have the amount of power coming in the north and the amount of power coming in the south are not the same, which gives us probably our orientation of our main magnetic field. And as they begin to equalize, this causes our main magnetic field to quote unquote weaken. But that won't stay like that. Obviously, it will switch, and then everything will flip, basically, because it doesn't take much to build that field back up. It wouldn't stop the field around the Earth, though. So.
Yeah, it's good stuff. It's fascinating.
I love that.
An onion capacitor is the way I look at it. It's a giant onion capacitor with an electric motor in the middle of it.
Actually, totally right. That is a really good analogy. Well, because there's multiple levels, multiple layers, totally. And so I see exactly what you're saying.
Giant liquid onions, if you want. Yeah, it's interesting. Well, so I guess it's both, right? You get the saltwater oceans, going through the mineral waters, deep in the core, right? And you get the dries, right? So it's a wet dry transformer, right? So I don't know how do you do all that, right? But it's interesting. The telluric currents, right? They follow all those paths. It's fractal. Who was doing the art earlier there? The drawing, was it?
That was Cameron.
That was me, Cameron.
What program are you using?
I use Krita for coloring. Krita.
Have you ever tried Blender?
No, I have not.
You haven't?
You gotta try Blender. Yeah, Blender 2.8, because you can do what you're doing and do it in 3D.
Okay.
You gotta try that. I'll show you here.
Yeah, actually, yeah. Sure. I gotta tell you that what you did there with that sphere was just amazing.
Well, this is different. This is the same program.
Same program? Yeah.
Same.
This is great. What is this program called? Blender, you said?
Blender 3D. Yeah, it's a Blender, but this is Blender 2.8. I'll share the screen and show you this.
Yeah.
Cameron will like this. So this is drawn by hand, sketching the same way you're drawing, right?
Oh, wow, that's cool.
But basically, you draw it by hand, and then it's a 3D model, right, in 3D space. Let's see.
That's crazy.
Oh yeah, it's crazy cool.
It looks like you're putting in. It looks like
I'm
you're
trying
to put a magnetic field in a magnetic field type of thing. Is what you're sort of
well,
drawing.
that is kind of what I'm doing on this one here. All that.
Woo, nailed it.
Right, so you can see how it'll record how you drew it too, right? More or less, it should.
I'm sorry, I'm not saying anything. It was just amazing.
No, that's fine. I'm equally impressed. This is.
I'm equally impressed that you made an entire model from this too.
I bet your gears are spinning in your own head there. I bet.
Oh man, I can do all sorts of scales now with this sort of program.
Object roll draw. Right. So if I go into, let's see, front view, for example, I'll just try and do a quick example. Right. So you can do basically freehand drawing, whatever. Let's see. So it's just a normal sketch program, right?
Right.
I'll go back. Just trying to get some programming in it.
Work your magic.
Let's see. Front. And add a new grease pencil here. And then we'll try to draw something, see what happens. All right.
Okay.
I didn't set up any colors, but let's make it a different color. Something green.
Sure.
Bigger. Right, so basically you can do a circle. There are ways to do a guided, like if you have an unsteady hand, right?
Right, of course.
Right, you can do a guided draw too, right? So I want to draw a circle, radius, parallel, grid, whatever it is. Right. I want to snap to all kinds of stuff, right? So I do a circle, I can do the same thing, and it'll make a perfect circle, right? Compared to my shitty circle, right? I can do a perfect circle, right? But it's an object in 3D space. So then I can say, okay, well, I want to edit that object.
Oh.
Right. So I can go into like an editing mode, as you could in any drafting program.
Right.
Let's see if I can get this to work now. Oh,
no wonder you didn't click it. That's why.
Let's see. Object mode should be. Let's see, grease pencil first. Edit mode. Depends on which way you get this thing going now.
I think you have trouble clicking the lines.
Well, yeah, it depends on. Sometimes I lock the layers too. Like, what did I do? There's a lot of stuff in it, right? Blocks. All right. Well, I'll just cheat for this one because I'm not sure what exactly it's doing.
That's okay.
I couldn't grab the point, right? Of course, going to give my 50-year-old eyes a break once in a while.
Oh my God! Recently, I was starting to wear glasses. I'm 45. I know exactly what you mean. Like I thought it was just. I was like, why are all these young guys having no trouble seeing this soldering? It's like, oh, like I'm getting blind. That's what's going on. Well, at least when it comes to close up, I'm a little bit farsighted, so I just need a little bit of reading glasses. That's about it. But still, it's disconcerting. Because I really like seeing things, you see.
So you can take, it's a 3D object, right? So once your eyes are adjusted,
once we
once we adjust your eyes.
What was that, Sonny? I can't quite see what you've done here. Anyway.
Yeah. You can take the object and then copy it and do whatever you want to it. You can modify it with anything you want. Right? Basically, you say, okay, well, I want to copy that.
Like a bunch of times in a rotation.
Like a bunch of times. Yeah.
I see what you did. I see. Okay, that would make the torus. I can see it. So you just drew the angle and sort of connected it, and then sort of went around in a circle from the top and sort of made the main.
So you can do any kind of modification you want to, right? So once you get the shape you want, right, you can do whatever you
copy it.
You can repeat it, copy it, move it, animate it, because it's a full D. Oh yeah.
I didn't expect the animation part.
Oh yeah, it's a full 2D animation thing, right? So if I take this object or 3D animation, for making movies. Right?
I was going to say, because I think I've seen people make stuff in Blender. Because the way you're talking is something. Yeah, you could animate with that. Yeah, wow, that's just. Well, it's amazing what you like. We didn't have this years ago, and now here we are here. You know. This would be an expensive power suite. Now it's a desktop program on a Mac.
Application. Well, exactly right. So you can draw your characters, right? And then I'm going to skip forward to say where I'm at. I'll go like 20 frames forward. Mm-hmm. I grab the object, bring it forward. Maybe up here a little bit. I'm just randomly playing with it.
Sure.
And location, rotation. So I'll just put in, I want location, rotation, scale. That's animated as a keyframe. Rewind it and hit play, right? So you can animate anything you want, right? Because it's a full suite. It's a full suite for making 2D animations, full 3D movies like Pixar, right? It's got compositing software, so I can go into a modeling mode, scripting modes, whatever, right? Texture paints for weight painting, gravity, animation. There's your compositor for your video, right? Everything.
We could actually make an interesting collage where you can take videos, like you could be doing an overall of like some of the special highlights of some of the shows, and you could move from show to show. But I think I could do that in After Effects too if I'd really tried. So this is much more powerful.
So this is what I'm trying to do for the EU meetup, right? Is it basically a hand drawn animation build starting with the Earth, right?
And the sun and so forth.
Magnetic field, the sun, then the solar connection, right? So I'm going to do a fly through.
Ah, right? Okay, I see what you're going.
This is just showing how it's been drawn. But yeah, it's fun stuff, eh?
Oh, just amazing, just amazing. I would love to see. I mean, especially if you could apply weights to that or something, like you can not just animate it, but because I think Dave was showing something in his work where he can do. You can give mass to things and watch.
Oh, I can do that too. Yeah, This will do full physics simulations and everything too.
Wow.
Right?
Okay. Well, that's just cool.
Let's open. Let's see.
And you can do full detail drawing and coloring of the objects too. It doesn't have to be just an outline too, right?
Oh, it's everything. Yeah, it's like full 3D shading with reflections, and it's got volumetrics in it for if you shine a light through a cloud, right? It shows how the light passes through the mist, and it's for making movies, right? So you can do whatever you want.
You can pretty much do a full-on drawing or painting with the program.
Oh yeah, you can do it. You can do it that way, or else you can do. Let's see.
You could draw the Mona Lisa, then animate it off the screen and make it bitch slap someone. Yeah,
absolutely.
What kind of an insane machine do you have? How much resources does it take?
Oh, I'm just using an iMac laptop. Yeah, that's it.
Any program working on Windows PC?
Oh yeah.
Oh, I'm sure there must be a Blender for here.
Oh yeah,
I bet you I can go find it. I'll do it after the show.
Windows PCs. That was its first format, and it'll do both Windows and Mac. Yeah.
All right. Oh, you can't see me right now, but I'm smiling very widely right now. This is great.
Okay.
I bet you are.
Right, so this is a physics simulation where I ran like the physics to make so the particles, nothing's being programmed here except for the particles, the weights and the mass, the gravitational constants, and then it over time develops a ring around like a Saturn.
I see.
It takes time though. But within 1,000 frames or so, you can see the particle system will start to form shape.
But is this based on physics, or what is this based on? Or
this is just purely physics, yeah. So you have like the sphere in the middle that has certain mass. I gave the gravitational constant. I gave the particles each their own gravitational constant.
So they're basically asteroids.
Asteroids, yeah. And then there's a vortex with current coming up through the middle, right? So there's a spin to the current, working current passes through it, and then eventually.
Oh, I was going to ask. I said, well, that was what I meant. Like, was it just because I don't know of any system that will make a ring just without something forcing it to the equatorial plane? But maybe I could be wrong. So, I mean, I'm hearing some math things. Eugene would definitely know, or maybe Jim.
Well, there's a harmonic resonance. You have to have a harmonic resonance in it to do the push-pull. And then there's the magnetic field that's also doing the push-pull, right? So it pushes and pulls in both directions, so you get particle separation.
Does it have like a physical engine inside of it, or you're just writing the code manually, or how does it work?
You can do it either way. It is Python capable, but if I go like to a physics tab here, I pick the field, right? I pick the field that I want, and with the physics tab, I say, okay, I want a force field with a point source versus planar source. It has strength X, Y, right? How much it perturbs. It's got all these settings in it.
That's pretty amazing.
Your fall off rate versus tube, cone, flat, whatever. And it depends on the type of field that you have. So I can go a charge. This is a charge field. Right?
Wow. Oh my God, this has everything.
Smoke, yeah, drag, turbulence, voids, whatever, right? Yeah. So this is just a quick.
I assume it doesn't actually have the ability to like do supersonic shockwave type stuff, because otherwise.
Oh yeah, you can, yeah.
Oh man, we could literally simulate blowing things off the face of the Earth. You know that, don't you? We could like make a landscape and blow it up. Not real life. Not real life. You know, like.
Let's see, toroid galaxy. So here's one. This one might be kind of cool.
We're going to blow
the same thing. So I get a double. You get a double vortex with a split, right? So they're kind of separated in the magnetic field, and there's a tilt in it. There's only 3 fields acting, no gravity whatsoever. Right? So this is in an anti-gravity field with particles, and you just hit the button and wait.
This is basically the simulation that what's his name did, Peratt, so to speak. Well, right. Not quite, because he uses 2 massive point sources as the footprints of the Birkeland current. Oh wow! Look at it, full of a funnel. That's just.
Oh, it gets better at the end. Yeah. Right, you can look at it any way you want, right?
Of course, it's trying to process that. I can see it going, hello, okay.
Yeah. Don't kill me now.
No, don't hurt me. Don't hurt me. It's like
so there's your 3D. There's your donut, right? There's your 3D toroid donut. Right?
Wow.
Built from 1 million particles, or however many I get in there.
Yeah, a ton. Probably not 1 million, but a couple thousand, at least. Maybe 10,000.
Yeah, might be 100,000. Let's see.
Well, I'm just guessing, but a lot. Well, you can actually find some interesting harmonics that you can start playing around with, like different resonances. You can build a model of the solar system, and
right,
and see, like what would happen over time, and especially if you can start incorporating magnetic fields and so forth into your model, as opposed to
Well, this one I got a vortex field that's doubled, right? So you get a split. And then I have a harmonic field that's running on pi, right? So 3.14. The vortex is 1.618 golden mean ratio. The harmonic is 3.14 based on pi. The magnetic field is 9, so 369 ratios for electricity. So another vortex is 3.6, which is a flow of 1.0168, right, which is the kind of an inverse ratio of the golden mean. That's pretty much it, right? Right. So the trick is you need to have a harmonic field that's running somewhere around the golden mean or ratio, and the fluid dynamics need to be about the Clauser constant, which is what is that? 0.53 or something like that. But you run from the golden mean reciprocal of 0.618 as your minimum to your maximum of 1.68. So you do a reciprocity, and you'll get it to work every time. You'll get this double layering in the surfaces, right? You can see, like, if that was a solid object, it would have a surface on the top, a split, and then a secondary surface, and a liquid core, right?
I'm not sure about that, but still, just being able to translate an actual formula into reality in a program such as this is a big plus. And with time and some detail, you could actually simulate like a current creating a supersonic shockwave across the ground. I'm sure Andy would love that. Just blasting.
Yeah. So if you can give me, even if you can draw it on, like if you draw it on paper, just say, okay, I want to tell me what you want, right? I want a sheet. I can do it over a landmass if you want. We can take like a map of the Grand Canyon and put a current across the top, right?
Exactly. I was going to say we can just grab like a small rolling hill mountain or landscape from Alberta and subject it to some horrifying electrical death and see what happens.
See what happens.
But we'd have to sort of layer it too, because it has to have mass and material, and we'd have to make it. The ground would have to be made of particles so it can be blasted, right? So,
right. So I just need
it'd be a lot of work, is what I'm saying. It would be
a lot of work, right?
I think it'd be fun.
To know. Just tell me the constants you want, right? So how much voltage, how many square kilometers, like what are I need the limits. So you tell me the limits and I can do the model, no problem.
Well, we're going to have to, I'm definitely going to, the moment I'm going to just go talk to Andy, because Andy was on I saw his comment there a couple days ago. He was like, hey, I'm on this podcast. He said something. I was like, I guess you are. So, I could shoot a message to him and tell him, like, hey, we got a friend that might be able to blow things up in a simulation for you, because he really would like to see if we can make a shockwave across a mountain range. I mean, we have a lot of evidence that is the case, but to actually put the constituents together, make a reasonable model, even if it's too much to be processed in real time, as this does, obviously, we can set it so that it would quote unquote render and then produce a video of the effect.
Oh yeah, this is set up for that too, right? I can render this out as an animation, and then
Perfect.
It should take 2 or 3 days or a week, whatever.
That's a bit more detailed I was thinking, but yes.
Yeah. Well, some of them do. I've done some renders that have taken days, right? So I'm always nervous I'm going to cook my processor because you'll hear the fan run every 2 days. It's like, oh, that's getting hot, right? But, so I set it up. I set it up by window. Yeah.
How do you clean your processors? Your fans and your stuff?
Well, I'll pull the back off and blow it out with some air, whatever, once in a while. But it's
besides that, which is obviously fine, I actually have recently taken to. I have an old toothbrush, and I literally go in there, take that cover right off, and I clean that CPU fan grate, just scrub it off, and make sure there's no dust in there. That has really cuts the noise down for me, anyway. So, but obviously, if you don't have any buildup on the back end, it's no big deal. So, I just happen to get it, like you have stuff for a long period of time, and you're like, you think it's like still clean on the outside, but you literally have to go and remove parts to see it, see the blockages, as it were.
Yeah.
But yeah, I've rendering video. I've done some of that. Like we were like, okay, this looks perfect. After so many hours of work, and then this back in the 90s, and I rendered it. Look, it did take like 25 hours to render on a 500 megahertz processor. With like 256 megs of video RAM or something. Poor thing. Didn't know what I was doing to it. Why aren't you playing games with me? No, just sit in the corner and process data. I love that too. So is that the equator versus what?
Well, I was just setting these planes up before we get on the call. So I'm setting up to have an equatorial plane and then the ecliptic plane and galactic plane, like Eugene had gone through his talk, right? So I can kind of compare what Bruce has got, compare what I've got, compare what Eugene's got, compare what everybody's got, right?
Oh, and if you're doing this, there's one that I think that you should probably go for then, because obviously Eugene's work is exemplary on this, but I meant that that Revelation of the Pyramids video talks about a alignment of buildings around the equator going from Easter Island across Peru all the way up into Giza, and then back down through Angkor Wat, and then back down through the South Pacific again. So it's 30 degrees off the equator. Now I don't know if that's even remotely even a real thing. Like, this could be bullshit type of thing, but it might be interesting to see what it does on your map. That's all. So.
Right.
How it pertains to these planes, or if it does, because if it is an ancient quote unquote alignment of maybe they were harnessing something, maybe they're doing something. Maybe the alignment mattered. I don't know. So, we're talking about people whose we don't even believe that they were. We fostered so much stuff on them since the 1800s or before that is just not real. So getting to accept that our ancestors were not idiots, like my grandfather wasn't an idiot. Is
that the one where they took like? Is that the one where they took like 800 of the temples and lined them all up to their respective north-south, right?
That's the Mario Build-Reps thing. That's fantastic too, don't get me wrong. But no, this was a video probably put out in mid-2000s, and it talks about the nature of the locations, like how there's pi and phi in the Great Pyramid and all this wonderful stuff, of course, as you would expect from any sort of show that says Revelations of Pyramids. But this was a worldwide connection culture thing that they were trying to point out, and they had an alignment of buildings around the world that seemed to be in a perfect circle type of thing. But, of course, like I said, may just be sensationalist stuff, so it's hard to tell nowadays. Something
I find that very frustrating too, right? It's like on the internet, you need to be an expert detective, and your discernment has to be like platonic, like you got to be like Plato and Socrates having a discussion in the cave to get the truth out of the dead. So, can you kidding me?
Well, and
eventually you'll get there.
Well, given the circumstances, it is a tough. It's a tough thing to go over. You're basically trying to decipher the biggest puzzle piece that ever was, our past, and only because some of the pieces are missing. No one recorded well. Some did, but the things that seem to be recorded well and diligently are the ones we consider myths. Like it's like like this god was doing this, this god was doing this. Oh yeah, they were just talking out their butts. Crazy primitive people. They were scratching on cave walls. That's so dismissive sometimes, because clearly they build monuments. They're not right. Building a monument without an engineer or someone who could at least calculate something. Unless you're just piling rocks up, you're going to have trouble. Unless it's a small building, but anytime you get to something large, we have to coordinate teams and stuff. It's not. it shows a degree of organization, especially to build objects that we cannot build today. Like maybe.
It's amazing, like, I don't have the answers for how some of that stuff is built, but it's almost screaming, variable gravitational constants.
Well, you're not going to find an argument from me. I scream that myself. I mean, the comet thing really kind of, like Wall Thornhill's like, this is not ice, this is a rock. I was like, you're right. That's all I really kind of, at the beginning, that's pretty solid, but even
200-ton dinosaurs walking around like they're on the tippy toes, right? So, yeah, okay, how'd they do that when their bone density isn't like titanium?
It's not even the bone density. It's a simple matter of if you were, let's assume that this, and I don't think it was 200, but I think there were at least 80 or something like that, but still huge. Or according to the calculations, as you know, but there's just simply not enough. There's no such muscles or flesh that can hold like 20 tons of bowels into a stomach. There's just there's nothing that's going to hold that. It's going to fall out. It's going to rip the bag. Like that's all I meant. Like you just can't walk around. It's I mean, like blue whales don't walk on land for a reason. They need to maintain themselves in the water. That's what's keeping them up.
Otherwise, yeah.
Well, this has just been fascinating. I'm so glad that I got a chance to see this. I wasn't expecting that. This is the type of, you're doing God's work, son. Like I'm just,
yeah.
You know what I mean? Like, getting to track the hurricanes alone and seeing the relationship and being able to model that with a volcano set and everything.
I'll see that there. That's kind of where it's good. I'll see it there.
I can see why Bruce was
is Eugene still on the call? I don't know.
Yeah, Eugene's right there.
Eugene's still here. He's just
yeah, I'm here.
Safe, yeah. Yeah, so if you're available sometime, and if you want to, we could. I'm trying to kind of take what you were doing with the planes, right, and then get them dissecting the globe in the right places. And I wanted to know which way do you think in the solar system? Like we're on the 60 degrees to the galaxy, right? Rotating around the sun. Is south, like is Antarctica the direction we're headed, or is the North Pole the direction we're headed? Where's the bias and the inertia?
Do you mean where we're headed with respect to what? Like in this hypothetical
the galaxy,
element?
The galaxy itself, right? So we're going around the galaxy. Which direction are we going? Counterclockwise or clockwise? And is the South Pole forward, or is the North Pole forward?
If you look from the North Pole of the galaxy, it's basically arbitrary, what's considered north and south. It would be clockwise, actually, somewhat counterintuitive, if you take into account that in the solar system it's counterclockwise. But if you're asking about the orientation of like the Earth's spin axis to it, that's a kind of a more difficult question. It's quite a large angle there, but I would see it's pretty close to the equator from how I imagine it, actually. Like if you plot the direction where the solar system is going around the center of the galaxy, it would be somewhere near the equator, I would say. But I can give you an angle, but I'll have to look into. Just
the general direction too, right? So the sun is basically going around in counterclockwise, I think, from the centers of the galaxy.
No, if you look from the center, it goes to the right. So if you look from the north, it's clockwise.
Okay. Yeah.
And again, it's kind of counterintuitive because in the solar system, it's everything goes counterclockwise. Well, if you look from the north.
out here.
That was just fantastic. I'm very. I want to see some stuff done with that now. I can just picture us or someone at the you or maybe you and Andy on stage or something at like some EU conference, and you're going. So this is a video that we made with Chris. Let me show you what happens when lightning blasts across the earth. You know, like and you get to do it in slow motion and watch little blocks get ripped up and stuff. People would love that, I'm sure. The visuals. And there's a lot you can do here. Those loops in visual form, that'd be great to see. Stuff like that. But see some movement or even grab the footage of a prominence, if you know what I mean, like, and then turn it blue and then put it on the water or something, that'd be kind of cool. Because, that'd be fairly simple. Sort of try to then look at it from the ground and see what it might have looked like if you were standing and say there was a loop that big heading across the Pacific, say, and then you were standing in like China looking at it. What it would look like, type of visuals that you would normally not be able to see, that type of thing. So what is this that we're doing? This is blowing my mind too, because now I'm just seeing all these lines.
Well, this is the same thing. That's why I was asking Eugene.
Where they?
Way, okay, so if I look at I just want to make sure I get everything going in the right direction, right?
Sure.
So,
But what coordinate system do you use? You could get the precise direction if you want.
well, I can. Well, what's his name? David, I think it is. David is. We're going to try and do some voxel programming, right? So I can actually take the stuff in voxel and dump it in here precisely. So for now, I'm just kind of working on some solid models just to get the orientations proper. So I can use any coordinates you want, but any scale, any coordinates, whatever it's in meters per second or it doesn't matter, degrees.
Mm-hmm. Well, I found it like it's not as trivial as I thought. To make coordinate transformations. It turns out that I've tried to develop an algorithm, and I thought it's going to be super easy, but it turns out not to be the case. I've already had a lot of headache with this arctan2 function. If you ever heard about that, if you're trying to make a transformation from a spherical coordinate system to rectangular or vice versa, there's a lot of ambiguity there, and you have to redefine many functions. Like you can't just take arctangent of x and y and get this phi angle. You have to be much more complicated than that, basically.
Yeah, I thought it'd be easy too when I first started with this. But you think it'd be simple. It's just a bunch of balls flying around in space. It's going to be simple. It's not. The biggest puzzle we've ever seen for such a simple form. So I'm just trying to figure basically, all right, so there's our plane for the galaxy, and we're looking at it from the top side north, right? And moment of zoom, it's going clockwise, right? So as long as we get that right, but then which direction, I assume we're going in spiral arm out here.
Okay, I was basically wrong. So the angle between the Earth's spin axis, so Earth's north, and our rotation around the galaxy is only 41 degrees. So it's somewhere in the northern hemisphere. Well, not an exact place because obviously Earth is rotating. So it keeps running on the surface of Earth.
At 41 degrees north?
Yeah, I would say that, my initial conclusion would be that it's 41. No, it's not 41 north because it's, the angle between the pole and this direction. So it should be, how much would that be? 49? No.
I know.
Yeah, it's going to be 49 north latitude, basically.
49 north latitude, okay. It's like 3 degrees north of me, I guess.
49 no gravity.
Yeah,
It makes a big circle in the sky.
As Earth rotates, it obviously would run across the whole this whole parallel.
But that totally makes sense because that's what we see when we see the Milky Way. It's like you can see a bright spot there somewhere, above you, and then yeah. But yeah, I think the bright spot is kind of sort of if the Milky Way is above me, then yeah, I think it's slightly, but like it's more right above my head.
Excellent.
I think for you too, somewhere in that area.
Well, see, I'm trying to bring into these models like you have to program in velocities and inertias, right? So in the mass of the fluids and whatever.
Right.
But I noticed, like, if you take a conducting, like a sphere of copper, right? Just a chunk of copper in a sphere and drop it through a magnetic field, well, obviously the currents, right, will develop in the copper, right? Conducted through a magnetic field. And those are measurable, but it's interesting when it's in motion, dropping freely through a Helmholtz coil field, well, then the currents or the density of current will be on the bottom, right? Always in the direction of force. So
you're talking about copper, Lenz's law.
Right, right. You take a sphere of copper, drop it through a set of Helmholtz coils, and the magnetic field, right, will actually be focused on the bottom. You'll have more current on the bottom due to Lenz's law and gravity. Like it's reverse of gravity essentially, right? You'd think all the charge would go to the top, but it goes to the bottom in that particular case, always in the direction of force. Right, so there's this parity or polarization in the direction of force.
I've seen them levitate quite heavy weights using that technique of magnetic fields and copper. Of course, the unfortunate effect is that whatever mass you are suspending, the resistance to gravity. So literally the same problem I have with so many other things, but with gravity, what is supplying the power? You have a force, give me the power. I want to know.
Yeah.
But in this case, there's a tangible effect, basically, by putting the motors on top, and you're basically levitating the motors as well. So it's about 100 pounds or so, 150. It gets really hot because it has to resist 100, let's just say kilograms for reasons, 100 kilograms, and then we can convert that to newtons, and then we can use the force of gravity and then convert that to newton meters. And then that resistance must be expressed in joules, and or is it watts, I guess, to resist that force, and it must be maintained. So this is the kind of thing that I think about when I think about gravity, if you know what I mean. Well, maybe the reason the Earth is hot is because the moon's here. All the other moons are really tiny. This moon's huge. Maybe it's messing with the Earth. Stuff like that.
Induction heating and resistance and induction heating and
that type of thing. Yeah, but I don't know if any of that is completely true because we're not even sure of the fields what they shape. But once we know the shape of the fields, then we can actually start doing calculations because it's a matter of if then. If the field is this much, if the distance between these two bodies is this much, then the amount of is this.
Lately, I've been leaning a whole lot more towards a phase hydrogen core, right? Not iron. I'm thinking more like phase hydrogen, just because this way stuff is working out.
I'm not even sure if it's even there. My idea is that there's no core. It's just an empty void. I'm kind of in that camp. No, I'm willing to accept. I'm not married to it. If someone showed, me and Eugene have talked before, where we were sitting there and going, well, is it the gravitational constant that changed, or is mass really changing? Those type of questions. Because you'd have to define the difference between the two is because one will affect inertia and the other one makes them balanced and all those things like that. So it does make a difference. And getting to the nitty-gritty is, we're just not there yet. But, I'm not going to argue with Robitaille either, but I also know that Robitaille has to exist within a framework. He has to resist with that gravitation gravity is universal. We don't have to play that in that world, only because.
Well, even with even if you say gravity is not universal, but it's relative to the amount of energy in the system, right?
Well, no, that's
as far as charge density, but
is the universal law of gravitation is not universal, is what I meant. The law itself, the G constant can change or something along those lines. If it's not universal, then what we know about space is even smaller than we think. Because although we do see anomalies, we do see other problems. We also see, in the local area when we're sending spaceships and satellites around, they seem to be doing okay. Although we do have the Pioneer anomaly, there's a little one there, and stuff like that. But to say for sure that, what could cause gravity to change? Why would a comet act as if it is made of snow? Perhaps maybe they're just really hollow. It would be ridiculous, but possible. But still ridiculous.
When I started looking at superfluids. Right now, I'm in the superfluid camp. I know it has zero viscosity and zero resistance to electricity, right, and reject all magnetic fields. So when you put electricity into it, the magnetic field is maintained, but friction isn't induced in the core, so which means that the crust can rotate around it with a whole lot of friction. But we know that there is retrograde motion in the core. Seismology, seismographs, it's rotating at a slightly different crust.
Well, so is that, see, I know that we have data sets, and I'm always willing to go over the data sets, but it's the same question. It's the same argument that I have with that is the same argument with subduction, we can't see it, but it must be there because our theory says, okay.
Yes.
So in this sense then,
I don't think subduction it's a thing at all.
No, I'm obviously with you on that. I just meant we see layers and we see direction, but the way that we're reading that direction is through electromagnetic situations. Perhaps maybe there is orientation to the next layer down of plasma, just like there is in the clouds above us and the surface itself. And perhaps maybe there is on the inner layer of that molten sea, I would assume, that is the outer core, there is that would be positive, and the other side would be positive. So you'd have literal positive charge pushing on each other. There would be a repulsion in that area. Perhaps that is the mechanism that allows us to grow, for example. Who knows? But stuff like that.
Well, there's always an exclusion zone right at a pressure transition point, whether it's electric or pressure, it doesn't matter, right? That's why we get crystallization and phase transitions in metals, in whether they're liquid or solid, doesn't matter, right? There's always a boundary layer because of a phase transition of some kind.
Oh yes, of course that does make sense when I understand what you're talking about. So.
Well, if you take, if you have two opposing magnetic fields, well, there's a phase transition in the middle where they can't collide, right?
Yeah, it's called the
transition zone is what I call it, but
Brock layer or something. Or there's a
they call it the exclusion zone if you're talking chemistry. If you're talking metals and metallic stuff, it's the phase transition. Face center cubic and boundary layer between face center and base center, right? But it's the same thing, right? Everywhere, right? The wave shall not collapse, Gandalf, right?
Right, of course.
You shall not pass. Right.
Well, and of
Black
course
holes
we
don't
do
exist.
see that. I think that's the boundary layer, obviously, of the of what we would call the magnetosphere or plasmasphere of the Earth versus the Sun, for example.
Yeah.
These, and of course the heliopause itself, and so forth. So, yeah, I think that it seems that we're obviously seeing those, but obviously because of the spherical nature of the bodies, each layer that we go down will be more concentrated than the next layer. because each layer would be
onion skin densities. Yeah.
Well, if you're, for example, vibrating the outer layer, which is the ionosphere, and you're sort of like, if you could imagine that there's a bunch of layers, like each one is a metal sphere on top of each other, like babushka dolls, okay, all the way down to like a marble in the center, a BB or something, okay, and then you know that every time it gets a magnetic field, it could heat up, right? Okay, so it's surrounded, it's immersed in the plasma, this collection of spheres that are all on top of one another. And then you have the ionosphere on the outside. We'll call it the plasma that's gathered up around it. And then it's vibrating, so you look like that. Well, every single layer in that is inducting with each other layer. Like it's just like a resonance of inducting layers, and each time the ionosphere moves, it affects every single layer on that. They're all going to vibrate. And I think this might explain why we, see earthquakes more at certain layers, even down as far as like 1,500. Well, we see them down to 750 kilometers at least, which is ridiculous.
Yeah.
But still, it's stuff like that you're starting to indicate that there's, like you said, the layers of the onion. So.
Yeah, I think you're right. Like these deep earthquakes are perturbations. Like a frequency, right? There's a parent frequency, an ultra low parent frequency, and every once in a while they just pop off.
Well, and of course, these layers can also short out to each other too, and each one represents a capacitor to each other too. Like it's there's enough evidence to see that we're beginning to see it in that aspect, but we still need more data before we could look at it as easy as we could as just simply as Birkeland wanted to in his dream there, as just a sphere floating in space, like just a metal ball, like Tesla said there, like the metal ball in the magnetic sea or whatever he said.
Right.
We're not there yet, but we're getting there. I think we're starting to see.
Well, it's a liquid metal ball in magnetic sea, or liquid metal dielectric ball, essentially, which is paramagnetic and diamagnetic in a sea of electricity.
I was being extremely simplified, but I meant that because obviously, the Earth is incredibly flat, and if you try to just see it as you would in a laboratory, and of course it's also spinning fast as well. So all of this plays many roles that we're only now beginning to figure out, which is why I find this subject so fascinating. What is it that you're sharing, by the way, if I might ask?
Oh, this is just you sparked a comment or sparked an idea. So the fish swimming in the sea, if it's a part of a fish swimming in the sea, right? But I was fascinated by this one, the way the results came out.
Oh, yeah, go ahead.
Because it's like, it reminded me of Victor Schauberger's fish, right? Trout. Okay. You ever see Victor Schauberger's trout?
I've heard the story with regards to, and we talked about before, with regards to moving upstream and so forth.
Just a second here. I clicked something and somebody is talking to me in French now.
May we?
I'll try. Start cheering.
Je ne comprends pas français. Oh, un petit peu.
Yeah.
That's all. It's unfortunate. We're so English, New Brunswick.
Oh yeah, it's a terrible. My French accent is terrible.
Oh, I know. I feel bad. I feel bad they had to listen to it. Anyway.
So this is just another particle simulation, right? But if you watch it form, electromagnetic vortex with a higher frequency harmonic and a little bit more force towards, I guess, it'd be in the right direction. What you guys are looking at.
So what is causing the teardrop shape? Why is it going in that direction? Is that the overall direction of current flow, or?
The current flow would be to the right, right? Basically, it's just pushing it to the right.
Okay.
To get the teardrop. And it's basically trying to envelop back on itself. So I have an inflow on the return circuit, essentially, right? So there's an outflow and an inflow. It's trying to pull it back from the tail, back to the front, where the mouth of the fish would be, right? And then it flows back up around the skin on the surface. And it's being there's a harmonic resonance.
Actually, I think the electricity would actually go in the opposite direction, but I think it would move the particles in the direction you defined. So
right.
I'm cool. This is a cool thing about the polarity of electricity, of course, because we actually made a mistake such a long time ago, and we still suffer from it.
Well, yeah, right.
Conventional versus natural electricity. Rule, right? Yeah, I know. Yeah.
Right. So I'm trying to use the right-hand rule here, so you basically have the current going towards your thumb and it's wrapped around 90 degrees.
Oh, yeah, of course, yeah.
The magnetic force is in the opposite direction, right? And it's the magnetic force that's driving the particles.
Counter MMF, yes.
Right. The backside. So that's what's happening here. So then when you hit it with a frequency, right? The frequency, it affects the surface skin of the layers, right? Your boundary layer condition. It creates like Kelvin waves. I call them Kelvin waves, which is the interface between the two layers, right? Kelvin waves.
I like how you can almost see a pattern and waves and ripples in it, you know?
Right, so it is the fish, right? It's like Victor Schauberger's fish that he used to describe with the double vortex, right? Because Schauberger said that, well, it's the river that makes the fish swim, not the fish swimming in the river. Because if a trout is in a high velocity stream, they open up their mouth and the vortex forms behind them and pushes the fish forward. It doesn't have to do that. Which is what this is doing. And if you look on the front, let me see, I'll show you the front here. It's a little hard to see because I don't have that many particles in there.
Oh, that's quite all right.
If I zoom around here.
Looking right up the
kind of let your eyes focus on that a bit. You'll see the swastika symbol basically spinning clockwise, right? You see the four blades of it if I deposit it in the right spot.
Warning to the viewers at home, this is just what you see. It's not a political statement.
not a political statement. No, it's like you can see the forearms, right? But it forms that.
I see the cross. I see a cross there. At least, for sure. And I was expecting to see, just like we see when we look down at that top-down view of the sun, where we see the, I guess you could say, opposing vortexes, or opposing swirls, opposing layers, opposing bands. Not sure what we see, but they're opposing.
Give me a line, maybe. Let's see. Maybe a bit more maybe in this program. Running the card. It's kind of hard to see, like I said, but you can kind of see it going around.
I see a pulsing for sure.
Well, if you kind of focus your eyes a little bit, then just try to see that there's like an iron going this way and one in 90 degrees to it, that there's one going this way, like where they're more solid, like they're more densely packed.
Yeah.
Right. You should see a positive image of basically which would look like the Big Dipper going around that center point. Right. Not necessarily a swastika, but it's that spinning four-bladed star. Right.
Well, I was going to say, I see a cross. Yeah. Like a four-bladed star. Yeah, cross. Like a propeller or something. Yeah.
Right. Yeah. Yeah, it is like a propeller, right? So that's because the perturbations in the harmonics acting on this vortex in pulses, right? So the vortex is constant, so it's trying to do a rotational constant, and then it's being hit with the pulses.
You know what you just figured out, right? Why Voyager crossed the boundary several times when it left the solar system? Because it's pulsing, and like I was like, it's pulsing, but I'm not sure why. Like I knew that there was a pulsing action to move these electrons back up to go back into the poles. Like that was the general understanding of the circuit, right? In the homopolar motor Faraday effect kind of way, or sorry, the Faraday motor kind of way.
That's what Bruce De Palma referred to these as torsional fields, right? So there's this torsional effect outside of hysteresis. That's the way we would say it. Right? But it's just a pulse, right? So
there is a hysteresis refers to magnetic field limits, but yeah, that kind of can play in a role because obviously there's flux involved here, yeah. And it is hitting its two limits, and there is a lag in each of the returns because it's not. It takes time for the magnetic field to affect all the particles again and turn it in the other direction.
Right. It's time sensitive. Yeah.
Well, it's the same thing that happens within even soft iron of the core of a magnet. As you know, that's where you get your hysteresis loop. So. But still,
I think it's the pulse. It's the harmonic frequency in the pulse is the primary.
Oh no! But anytime you have a change or lag in a system, and which by the way is not a very big one. That's you're talking about the magnetic field having to affect everything, and everything sort of rearranging itself to the new field. That's that delay. Like that is a fairly small delay, so it's just nothing can be helped. It's just what it is of the effect of moving a field across something and going, oh, we're all polarized north to south now? Okay, we'll just eye-line ourselves that way now. And that's all they're doing. You know, and then of course, oh, we're going the other direction? Okay, we can do that. And they do that. But that is what is causing some of these lags, which of course is going to create some harmonics, but not necessarily, those are just mass delay harmonics, which would pertain to how big each mass is and all that shit. So, anyway. Babbling on for over nothing. I'm saying your stuff's great. Is what I'm saying.
Well, it makes I'm trying to the way you say this. It makes sense to me, right? So I'm just trying to bounce it back to you. This is my interpretation of what you just said, right? To confirm it is there's a time delay in the transition between, say, polarization of an iron atom to the magnetic field.
Correct.
It does take some time for that flip to occur. To change the polarity of the field, there's a time delay for the change of alignment to happen, right?
And if you plot that change,
so if you, right?
Sorry.
Now if you're trying to pulse DC current, right? You're pulsing, right? On off. Well, some of those atoms will try to return back to the parent current, which is the Earth itself or space, right? Mm-hmm. So they'll try to realign, and if you're pulsing that, depending on the mass of that individual atom, which is now trying to align to that current, it might take a little longer for it to try to realign, right? So you'll end up with misalignments, and the actual shape of that liquid metal, if we look at it as a liquid, will cause this to happen. So you'll end up with physical form coming out of a magnetic alignment within that structure because of the harmonic frequencies. Right, so if I took this particle system and gave each one of them physical form, you'll end up like with a pine cone, right?
That's actually very interesting. I was wondering if the pine cone was something that you were seeing there too, but the
well, it's exactly it, right? It's a pine cone, it's the trout, it's a fish, it's the petal on a cactus, it's a burdocks flower, it's whatever. One of the basic fundamental forms.
Aleutian hand axe, I should say.
Well, exactly right.
But there's but anyway, if you plot that change in the orientation versus its change in the other direction, right, over time, you'll have one S curve, right, on one side of the as it begins to turn, and of course the middle point will be slightly off to one side across zero. So this S will go up. That's one side of your switching of the magnetic field. And then the other side is slightly delayed on the other side of the zero line, on the other side, and that is your weird looking S is your hysteresis loop. So that's what that's called. So that is why there is that delay, and that's which is basically exactly what your friend said. I think I didn't catch his name, De Palma or something.
First De Palma,
yeah. That's when he said hysteresis. That clicked in me as what I'm looking at, because I was like, shouldn't this be instantly reacting? And I was like, no. Orientation of magnetic fields is a delayed effect. Oh, right.
Yep. So can you see my little arrow there?
I can.
Right. So you're describing that S shape, right? So you have a double. You get the spiral on this on the left-hand side is more prominent in this particular orientation.
I can see
right?
there's like pulses
right.
across it. Yeah.
Right. So if I draw those S shapes out in a three-dimensional sense, right, you'll have one that's a primary, and then the other one's slower, and it does this weird backtrack in the pine cone, right?
Which is probably the golden ratio in its reverse.
It probably. Is. Yeah. Exactly. Right. Yeah. It's wild, eh?
This is blowing my mind that you're actually modeling that. Seriously, I'm very impressed by this. I am so thankful to have seen this today.
Yeah. That's really cool.
I might actually, I'm so excited about this. If you don't mind, I might combine the last show with this one and put them both together because we have enough footage because that one was a short one and this one we did a little talking at the beginning. So I don't know, just an idea.